Okay, we're going to go back now to homework 2, where we were finding plant cells in an image automatically. And if you recall, the way that we did this was we turned that image into a grayscale image, where 0 meant completely dark and 1 meant very bright. And we said, okay, I'm looking for clusters of pixels that are all connected to each other and which are all above some threshold. And so I showed you if you do that, so here are the clusters that you find that are all above some brightness threshold, and you could say, okay, I'll estimate each one of those to be a cell, and I will report the center, the average x-coordinate and y-coordinate in each cell. Now the way that we tracked what was in each cluster was by using union find. Every pixel started off as its own set, and we unioned the sets that were connected, that were next to each other, and which were both above the threshold. So we would union the pixels that are in the same cell, being above that threshold and directly next to each other, left, right, or up, down. But I'm going to show you an even easier way to do this using depth first search. So I'm going to redo homework 2, but it's going to be a lot simpler. We're not going to need union find at all. We're actually just going to treat this image like a graph, where each pixel is a vertex and 2 pixels are connected if they are left, right, or up and down neighbors. And then we'll do breadth first search on this graph. So the idea is if we come across a pixel that is above a particular threshold, we'll do breadth first search or depth first search to travel to all the pixels it's connected to that are also above that threshold. So that's our strategy. So I started off with basically the starter code for the assignment here. As I did before, I'm gonna define 3 states: untouched, frontier, and visited. And what I'll do is I'll make an array that's parallel to this grayscale image. So this is what I'm going to pass in. It's called I here. It has m rows, so I get that with shape 0 for a NumPy array. And then it has n columns. And the first thing I'll do is create an array that is parallel to the grayscale image, I, and which is used to store the state of each pixel. So each pixel starts off as untouched. So I'll say states is equal to untouched times mp.ones mn. All right. So that is how I will initialize this parallel array that's going to keep track. So before, I had these all in a class, but now I'm just going to, I have the image and I'm just going to make a parallel array. Okay, now here's what I do. Step 2. Loop through all the pixels in the image. When we find one that is above the threshold, initiate a breadth first search, or let's say a depth first search from that pixel. Okay, so let's see what I mean here. So I'll say for y in range m. So there are m rows. I'll say that that's the y coordinate, and then I'll say for x in range n. So if I come across a pixel that hasn't been visited, so if I say if states an index y and index x, so row y, column x, if that is untouched, then and states y, and actually the grayscale image at row y, column x is greater than the threshold. So if we come across a pixel that should be inside of a cell and we haven't touched that pixel yet, we will do a depth first search from this pixel to find all other pixels that belong to the cell. So what I'll do is I'll make a list. So I have this thing I'm going to fill in here. It'll be cell centers. That's what I'll be returning from this. Let me make a little list here, or actually maybe I'll count the number of pixels I come across, and then I'll say maybe x total and y total. And so what I'm going to do is I'll do this depth first search and then keep track of a running sum of all x coordinates and y coordinates in the cell. And that'll allow me to compute the cluster center. Okay, so let's do the depth first search. So what I have to do is create a frontier, and because I'm doing depth first search, I'll always be adding and removing from the end, so I can use just an array list, just a list as the underlying data structure. So frontier is going to start off with, and maybe I'll just make them tuples here. So it starts off with y and x on the frontier. So the location yx. And if I look here, all right, I'll be doing. Let me maybe just copy and paste a little bit of this code, and I'll just tweak it a little bit. So as long as we have something on the frontier still, I'm always going to do depth first search. So I'll just say. So here, what I'll do is I'll say maybe I don't know. I have to come up with the name for the x coordinate and the y coordinate from what I'm removing from the frontier. So this is an O1 amortized thing. And so maybe I'll say, I don't know, this x, this y, or something. Or this y, this x. And so now what I'll do is I'll say, okay, I want to say that this was visited. So I will go into the states. I'll say states, this y, this x is equal to visited. So I'll remember that. I don't need to print it, but what I will do is I will, once it's been visited, I will add its x coordinates, y coordinates. So I'll say num plus equals 1. So I've seen an additional cell, or seen an additional pixel in the cell. So accumulate its x and y coordinates. So here I'll say x total plus equals this x, y total plus equals this y. Okay, and so now I need to look at the neighbors. Let me just get rid of this because we kind of already know this, just to make the code a little shorter. And okay, so what I need to do is look through all the neighbors here. So here's where I got to do a little work specific to this problem, because I want to consider all the neighbors that are above the threshold. So, okay, so a couple things I got to do here. So I'll say for n in, so we're going to want to do, actually I'll say maybe nx and y, or ny and x in, so we'll look, so we're iterating through these pixels from the top row down. So I'll consider neighbors that are to my right and below me. Let me think, is that enough? That should be enough for this to get everything in the cell. So let me consider the neighbors that are, so I'll say this y plus 1, this x plus 1. No, this x. So that's the neighbor right below me. And then I'll also consider the neighbor that's directly to my right. So this y, this x plus 1. So those are the two neighbors I have to consider. Just to draw a little picture here, it's like, here I am. I'm going to consider this neighbor and this neighbor. And I'm going to try to branch out to those. And then once I'm here, that can branch out to its right neighbor and its down neighbor. And I should be able to reach everything in a cell from that. Oh no, I should be a little bit careful, because the cell could actually extend to the left. Yeah, so just to be safe, let me look at all the neighbors here. So here's the one below, here's the one to the right. I will also look at the one above, just for the heck of it. And then the one to the left. Okay. So those are all the possibilities. And actually, I want to make sure that not only that I'm not already on the frontier and that I haven't been visited, but also want to first check to make sure that this neighbor hasn't, that this neighbor is actually above the threshold. So assuming that this neighbor is inbound, so say if ny is greater than or equal to 0 and nx is greater than or equal to 0, and ny is less than m, and ny is less than n. So if it's in bounds, then we'll check. If it is actually above the threshold, And then we can look and say, okay, and let's make sure that it's not currently on the frontier. So I would say states and y and x. It's not on the frontier and it hasn't been visited. All right. So that should do the trick. And I just need to change this now too. So I'll say, okay, if this is the first time that we're seeing this thing and we're going to put it on the frontier, then I'll change its state to be on the frontier. So I'll say states and y and x is frontier. And then I'll say frontier.append. This is O1 amortized. Since we're using an array list, I will add this to the end, and y and x. Okay, so I do that, and it branches out and visits everything that's connected to it that's above the threshold. It marks every pixel as visited once it gets there, and then it accumulates its coordinate. And so once this while loop ends, I want to add to my cell centers the pixel location, x total over none, y total over none. Okay, I think that's it, but let me see. So again, we're doing just a depth first search starting at every pixel that hasn't been visited yet, and branching out to all the neighbors that are above the threshold and actually inbounds here. Okay, let's see. Probably not going to work. Oh, okay. I should, let's see, get cluster centers. I need a threshold. Okay, let's see. Index 400 is out of bounds for axis 0 with size 400. So I thought I was careful here, but oops, I said ny is less than m, and I meant to say nx is less than n. Okay, we're getting close here. Of course, I should return the cell centers when I'm done. Okay, return cell centers. Okay, it looks like I'm really close. It looks like I might have gotten the x and the y coordinate flipped here. So let me see if I made this. I guess I was expecting maybe the first in my plotting here, my first coordinate to be y. Okay, anyway, yeah, there we go. So there's a solution to the cells problem that doesn't even have to use union find. And it's very efficient. It only loops through each pixel a constant, it only touches each pixel a constant number of times, right? Because each pixel is going to go through some frontier at some point in some search, at most once. And you know, each pixel is part of up to 4 different edges, if we consider that, you know, above, below, left, and right. And so it really is quite efficient. We just needed to keep track of one extra 2-dimensional array to keep track of what state the pixel was in. And there you have it. So don't get too mad at me that I didn't give you the easier way first. I mean, this does require more background about graphs and things like that. And I also wanted an assignment to show you union find. That was important. But moving forward, anytime that you have to find these kind of islands, you know, anytime you have to find these kind of islands of connected components in a graph, breadth first search and depth first search are great hours to do this, and this is the sort of code that you would want to write to do that. So have this in your back pocket. I was actually asked a question like this on a coding interview once myself. So it's a good thing to be able to pull out breadth first search and depth first search in an interview. Okay, but now I want to continue on to some other graph topics.